Hello, everybody, over there in Central Park, South Africa, and welcome to CERN. Welcome to specifically the CMS experiment at CERN. I am sitting here in the control room with my colleague and good friend Andres, and we are going to take you on a virtual visit of the coolest experiment on the planet today. So Andres is going to be your guide underground. We're going to follow him along with the camera, so you'll be able to see exactly what the experiment looks like. But let me first, while he's busy getting kitted up in his safety shoes and helmet and everything, let me first give a little bit of an introduction to CERN and tell you about the Large Hadron Collider and this experiment that we work on. So CERN was founded 70 years ago now, just after the Second World War, as a means to try to bring European knowledge back to Europe, and really found a center that whose job was to work on, at the time it was nuclear scientific research, but specifically for peace. And to foster collaborations among all the countries that were left divided after the World War. So 70 years later, CERN is now still pushing the boundaries of science and technology, and we have the biggest and highest energy particle accelerator in the entire world. It's called the Large Hadron Collider, and this is an overview of the Geneva region. Over here, what you see is the Alps in the background. That's the Mont Blanc, which on a clear day, you can see this really, really pretty peak. We have Lake Geneva over there, and you can even see over here, that is the airport. That's the runway, if you ever come flying into Geneva. And this yellow ring that is drawn on the surface is showing where we have the tunnel, roughly about 100 meters underground, that houses the Large Hadron Collider. So this is just a cutaway view of that. So the Large Hadron Collider is a 27-kilometer long ring. Its entire job is to take protons, speed them up to 99.9999991% the speed of light, and smash them together. And that's the job of the collider. That's the job of the accelerator itself, is to speed up the protons and smash them together. And they get smashed together at 4 places around this ring. And us experimentalists want to know what happens when these protons collide. And so at each of these 4 points, we have built basically, essentially a gigantic 3-dimensional digital camera that takes snapshots every 25 nanoseconds as these protons collide. And we have 4 experiments: Atlas, which is where I actually did my PhD. That was the experiment I did my PhD on. CMS. Zoltan's going at me. CMS, which is the best and the most prettiest detector, which you will see today, as well as 2 other ones called Alice and LHCb. And if I show you, so here are some schematic pictures of each of these detectors. And so CMS is the prettiest one. The names all come from acronyms. Some of them are a little bit silly, but the CMS acronym stands for Compact Muon Solenoid. And it's compact because it's about 15 meters from top to bottom, and about 25-ish meters from one side to the other, and it weighs 14,000 tons. So that's quite a lot of material to squish into such a compact form. The M in CMS stands for muon. Now, a muon is a type of particle that we can detect or measure coming out of the collision point. And the S stands for solenoid, because we have the second strongest solenoid magnet in the entire world, Our magnet goes up to 3.8 Tesla. And the magnet's job is to bend the particles as they travel through the detector. And because we have such a strong detector, we're able to bend muons really, really well and tell the difference between these type of particles. So I think Andres and Noemi are still there. So I guess I can chat some more in the meantime. But if you guys have any questions, feel free to stick your hand up, wave your hand up, and maybe somebody over there, if you have a question that you want to ask at this point in time, by all means, let me know. Okay, so let me tell you a little bit about how we detect particles. So first of all, we are smashing protons together most of the time in the LHC. Now, if you think about it, so let's go back. I think we're all probably pretty familiar with the concept of atoms. So never trust an atom because they make up everything. So atoms are comprised of a nucleus, and then you have electrons orbiting around them. And the nucleus is made up of protons and neutrons. So, when people talk about things like splitting the atom, what you're really talking about is taking the protons and neutrons and breaking them apart. Now, protons and neutrons themselves are actually made up of smaller particles called quarks. And when we are taking protons and speeding them up to the energies that we do inside the Large Hadron Collider, these protons, when we smash them together, the protons break apart, and the quarks and the gluons that hold the quarks together, those are the things that actually collide with each other. And they can create a big mess in the detector, lots and lots of particles flying outwards. And if you think about it, we are basically like forensic scientists. You know how, imagine you come across a car accident. You've had two cars that have smashed together and collided, and bits and pieces of car have gone flying everywhere. And your job is to collect up all the pieces and kind of put them back together and tell us what kind of cars were they and how fast were each of these cars going, and what happened when they collided. That is basically our job as particle experimental physicists. So I think that Andres and them, they should be close to the, are they heading off down underground?
Yeah, we can call them.
We can find out
But
where
in the
they are.
meantime, let me show you an event.
Yes. So this is a picture of what has happened after two protons have collided inside our detector. Each of those yellow lines is a particle that has gone flying outwards from the collision point and given us some signals in the detector. Here we are. So here, I'm going to pass it over to Andre so he can explain what he is doing over there.
Hello, can you guys hear us?
Yes, loud and clear.
Yes, thank you.
Great. So yeah, Noemi's just going through the personnel access device, and we're about to take the elevator down. So we're going to be taking you guys 100 meters underground. And yeah, we're about to get in the elevator. Yeah, welcome to CMS. We're going to go see the underground areas. There's a lot of activity and a lot of work happening at the moment. So we're not going to go to the floor of the experiment, but we will be in the balconies around to show you. And we'll get in the elevator, so we will lose you guys for a few minutes or a minute or two. But yeah, maybe back to you, Claire.
Cool, no problem. So let me give you a bit of an idea of what you're going to see when you walk into the cavern with Andres and Noemi. So the way that we build our detector is in a number of different layers, and each layer measures something different about the particle as it travels through. And when we put all of this information together, we're able to tell what type of particle it is. So right in the center, we have a silicon detector, basically kind of like this, the silicon pixel on your camera. And its job is to give very precise location information as a particle moves through, so that you can draw the track. It's kind of like a join the dots thing. So that's the tracking detector right on the inside. Around that, we have what we call calorimeters. Now, the calorimeter's job is to stop the particle. So imagine now you're back in your car, and instead of crashing into another car, you crash yours. Really, don't try this at home at all. This is purely a thought experiment. But imagine that you drive your car into a brick wall. Bam! And the bricks go scattering forward. You could tell how fast you were going if you counted up like all those bricks and how many bricks there were that got scattered and how far they got scattered. And our calorimeters do that, but instead of bricks, they scatter light. So by counting up the light, we're able to tell the energy of the particles. Oh, look, we've got Anders back again. What are you doing?
We are 100 meters underground. Actually, you can't see it anymore, but 97 meters underground. And we're in the floor of the experiment. We're about to go through the axis for the experiment. So this one, you might see that this is a different color. The one on the surface is green. This one is yellow. That indicates that if we were to try to open this door during collisions, it would abort the beams. But since we don't have collisions at the moment, we are ramping up the LHC in a month or two. So for now, we can actually go in. And with this axis, you can maybe see that it actually takes a photo of my eyes to make sure that I am the person who my dosimeter says that I am.
If you've watched Angels and Demons, this part of Angels and Demons where you actually need to scan your eyeball is true. However, your eye actually needs to be attached and have blood running through it for this to work. So don't think you can come and like dig out our eye and sneak your way in underground. It's not going to work.
Yeah, please don't. Yeah, so we, as I mentioned, we are just going to go up the stairs and go to the balconies. We can show you the view from, let's say from below, from the floor of the cavern, but there's a lot of work going on, so we won't stay and walk around in the floor of the experiment, but it should be a very nice view. And you can see that we have to go sort of around this labyrinth, if you will. So our experiment is also shielded. So there's a very thick wall that separates our detector from the service cavern, as we call it. So you can see that we have to walk all this way to get around this wall. And so here we are. And yeah, welcome to CMS. Oh, well. We might need to wait a second. As I mentioned, there's some work going on, but let me check. And yeah, I think it's because of the crane. So we might have to go around. We have to ask. But you can still see the detector now. So you don't get an excellent view just yet, but I promise we'll get in there.
So so the LHC kind of tries to run as continuously as possible, but at the end of each year, we actually shut down for maintenance and repairs and that sort of thing. So that's actually what's happening now. We do it at the end of the year, mostly because electricity costs increase a lot in Europe over the winter, and it does take a lot of electricity to run the LHC and its experiments. So that's why we do a lot of this maintenance work during this period of time. Let me see what else can I tell you about the detector. So we've got the tracking detector on the inside, and then we have the calorimeters around it, so the tracking detector will be able to see the paths of particles as they move through. And then around that, we have calorimeters. so we can measure the energy by stopping the particles. Now, remember these guys called muons? These muons are basically like heavy electrons, and they actually travel all the way through the calorimeters. And so on the outside of the detector, we build really big tracking detectors, basically. And their job is to just detect and catch the muons, measure the muons as they travel through them. So literally about, the whole outside half of the detector is dedicated to measuring muons. And you can see that like the different ways particles will travel. So a muon will travel all the way through the detector and leave signals all the way out here. Whereas an electron, for example, will travel just through the inner part and then get stopped in the first calorimeter layer. And this is how we're able to tell, what the particles are that we are measuring when we put all of this information from all of these different layers together. So I think let's go back to Andres, because he's one floor up now.
Yep. So we're one floor up, and you can see this is the elevator shaft. So we are at the moment 87 meters underground. And you can see these very nice LEDs that Sultan put together. These are meant to represent the data flow going up to the surface. So again, we are now in the service cavern, and you can actually see the detector on the other side of the wall. So there's an opening so we can take material in and out. But of course, once we start running the detector, we will cover up this hole in the wall. And this maybe gives you a glimpse of, again, this wall that I was talking about that separates our experiment, which is about 7 meters thick. So we'll go through the racks here, and we'll go around to show you the detector. So we have a lot of service racks for high voltage, low voltage, and detector readout, protection for the detector. So there's also detector safety systems here that you can see. And this is meant to keep the detector at the temperature, humidities, and anything you can think of. We have to monitor and make sure the detector is at a safe operating status. Otherwise, we have to take action, and that needs to happen automatically. So it's unattended, and it needs to be as reliable as it gets. So we have all these systems to monitor and then take action in the event that there's a problem with the dry air, for example, then we have to change the temperature of certain parts of the detector. So we're gonna walk through. We can come back to USC if there's anything we want to show or any questions.
Do we have any questions at the moment? Nope, I guess not. All right, cool.
All right, so we're gonna access the experiment again. So let's hope that we have better luck this time.
This is a day in the life of a physicist. You never really know what you're gonna expect, and you sort of just kind of have to make things up as you go along. If we knew what we were doing, it wouldn't be called research. Here comes Noemi through the doors.
Angels and demons.
Yeah. So these are all safety procedures. What CERN does is restrict access into dangerous areas. But once you are inside, then you are always able to exit without having to go through any authentication procedure, so that in the case of an emergency, you're able to leave immediately. And ta-da!
So here's our detector.
Yay!
So this is what CMS looks like. We're almost ready for collision. So there's still a bit of work to do before we can have the detector ready to record proton collisions. So the detector is just about close, but you might appreciate here that there's this orange shielding and this has to unfold into place to sort of cover up the beam pipe that you see here. So the beam pipe is of course the path through which the protons travel, and we have protons going in either direction, and they collide in the center of CMS. So we're standing now in the visitors platform. The very nice thing about the virtual visits is we actually get to show you not just what the visitors see when they come here, but we actually get to show you inside the detector, and we'll go through and we'll walk around the balconies. So Claire, if there's anything you want to point out along the way, let me know.
Sure.
Do we go this way?
Yeah, maybe if you just peek down, you can get a sense of the size. Those are people down there working. So that gives you an idea of the size of this thing.
Yeah, so since we're here, we're not going to walk in the floor of the detector, but you can hopefully tell that there are these orange feet just here. So these orange feet are actually air pads, and CMS is modular, you know. We have about 15 slices, and each of these giant wheels we can move, and in order to move them, we send compressed air through these air pads, and it's about 50 bar of air pressure or so. And that allows us to lift each of the slices a few millimeters, so maybe tens of millimeters, so that we can then pull them. You can see there are these metal cables that attach to the blue winch over there in the corner. So that's our mechanism to move the slices. Maybe I can also point out that there's this yellow doors. This actually is a garage for our hydronic forward calorimeter. So there's a very large detector in there. Oh, we can go, yeah, we can look inside. That would be great. So
Cool.
let's go down and we can show you HF. So that will come out once we have well, there are supports for HF that need to be craned down, and maybe we can quickly show the shaft. So this is the main shaft of CMS.
So as
And
Andres,
so,
oh, sorry.
go ahead, go ahead.
So Andres mentioned how CMS comes in slices. So you could imagine like a big Swiss roll cut into 15 slices. The heaviest slice weighs 2,000 tons. And these slices were assembled at the surface and then lowered down through that shaft that you are looking at now. One by one, it took 10 hours to lower one of these slices down.
Okay, so let's go ahead and go around the corner here and show you the HF garage.
Hey, I've never even seen the HF in the garage, I think. So that's cool.
They will not enter even now.
So we will
know.
not enter.
You see?
Oh,
I don't know if the door is even unlocked. Maybe we can open no, it's locked anyway, so we can't go in. But you can see through the opening here. So this is the hadronic forward calorimeter. So this is a detector that's made up of steel absorbers and quartz fibers. So the active detector material is quartz fibers, and we use steel as an absorber. I think Claire was talking about the calorimeters already, but this is what we call a sampling calorimeter, in the sense that we have these layers of steel that will slow down, not even slow down the particles, but they will interact with the particles. Like, so the particles come in and they produce a shower when they hit the steel, and then the next layer is this quartz material that will basically detect this shower of particles. And this is our forward detector. Forward just means that it's in the direction of the protons. So all this, the area where we are, this is the -Z side of our detector. The other side is the plus side, which we try to enter unsuccessfully. And yeah, in the minus side here, all this region is what we call the forward region. And so in probably a week, we will have supports here on the surface for HF, 2 weeks. We will have supports that currently are on the surface. They will have to be craned down, and HF will sit on top of those supports. Yeah. Yeah.
So yeah, what you're seeing there is that big red thing is
Yeah. So
the
Noemi's saying they will have to open it.
Yep.
again.
Yep, this will be pushed back
The
a little
shielding.
bit.
Yeah, just to
Ah,
push
right,
it back a
yeah.
little bit. Yes.
Yeah. Awesome. Yeah, and that's the beam pipe over there. So it's really small. Actually, the beam pipe's only about a centimeter or so wide, and that's where the protons travel. In actual fact, for most of the way around the ring, we have the Large Hadron Collider ring. We have two separate beam pipes. So the protons travel in opposite directions, one direction in each beam pipe. But just before they enter the detector, those two beam pipes merge into one. And that is what allows the protons to collide inside the center of our detector there.
So yeah, the center of our detector is maybe, I don't know, 10 meters in front of us. So it's 10 meters into the detector that you see in front of you. And it's also interesting that the beam pipe is made of a material called beryllium. So beryllium is it was selected as the material because it is lightweight enough that it is as transparent as possible. So when we have these collisions happening in the center of CMS, we don't want them to scatter because of the beam pipe, right? So if they hit the beam pipe, we want them to interact as little as possible with this beam pipe. And so we have this very lightweight material, but it's still a metal and it still needs to be, support its own weight and keep its, I mean, it needs to support a vacuum as well. There's a vacuum inside the beam pipe. But yeah, it's also difficult to work with beryllium. So this beam pipe was replaced around 2020 or 2021 during the long shutdown. And yeah, this was actually replaced so that it can accommodate the next generation pixel detector and pixel and tracker that is going to come in. We should discuss the upgrades at some point, Claire, but this is sort of a hint towards that.
Right. Yeah, so detecting particles is actually a really, really tricky business because they're really, really, really small. And the problem with something that's really small is that when you measure it, it changes its behavior. So sometimes you can use this, for example, like in the calorimeter, you measure it by stopping the particles, and then the information that you get from stopping them tells you about the energy. But for example, if you want to know the position and the tracks, what you really want is for your detector to affect the particle as little as possible as it's traveling through. And as Andres says, this is from the beam pipe all the way through, like the silicon tracker, for example, is also designed to kind of. And now imagine, if you think about it, so we have a magnet that needs to be cooled down with liquid helium. So we have cryogenic lines. We keep the tracker at minus 25 degrees. So we've got gases and everything pumping in there. We need like electronics. We have high voltage channels. Some of the muon detectors sit at something like 18,000 volts. So you have to have all of these high voltage lines going in to power them, plus all of the safety systems. And all of this is just stuff inside our detector that is not contributing to the measurements themselves. It's essentially dead material. So building a detector is a really intricate business because you're trying to maximize the amount of stuff that can actually measure the particles, and minimize the rest of the stuff that's dead material, but you need to have a balance between everything. Look at those tiny people down there.
Should we go? So we're gonna go around. We're gonna go through the detector, and then we're gonna go up.
Yeah.
And I wanted to give you guys a sense of what one of these slices look like. So between my arms here, this is one of the end cap slices. And you can actually see that we're not fully closed yet. Noemi was saying that we're going to open up for an intervention for one of the muon systems, the RPCs. And you can actually see some of the modules here. It's a bit dark, but hopefully you can appreciate that there are these rectangular-like modules. And these are part of our muon end cap. I can also try to shine some light. So hopefully you can see a little bit of our detector. There's also, I mean, there's a few things that might be difficult to point out, but there are these tubes that are sticking out, and these tubes will be in contact. You can see that they have like a black tip, and that will be in contact with the slice that is just to our right. So these, you can hopefully tell from this that our detector is really when we close it, it's really sealed shut, right? So it's really in contact, and you can
Really
see
compact.
really compact. Yes, of course, and you can see, I mean, the amount of space we have here between the slices. So it's really kind of difficult to show you what's going on between them, but I think already by this slice, maybe that's the tip of the magnet, right? Is that right?
I
Yeah,
can't
so this
quite
is
see.
barrel. So
see.
our detector is, of course, like a cylindrical onion, right? And then we have the barrel section, and then we have the end cap section. So this slice towards the left, that's all the barrel area. And then we have the end cap. So we have 3 slices for the end cap. And this slice that's part of the end cap, it contains what we call the end cap calorimeter. And so this is a calorimeter that sticks out, and it goes into the magnet when we close the detector. So again, thinking of the upgrade, so that's one item that we will replace, which sounds kind of trivial. It's just an item that we will replace, but this is extremely complicated. This is a massive project involving, I think you could even say thousands of people, maybe not, maybe around 1,000. I don't know. It's hard to say, but it's a massive project. I think in terms of complexity, you can say it's like building a satellite, and that's just like to replace one part of our detector. We're also replacing the innermost part of our detector, which is the inner tracker. And that's, again, an immensely complicated project. So of course, we won't be able to see it. We've closed the detector. And even if the detector was open, this part of the detector is sealed. So we normally don't access that part of the detector unless we really have to.
Yeah, I mean, just because we can go down underground here and put our hands on some parts of the detector does not mean that we can actually access all of the detector. In some parts, like the really innermost parts of these of this detector, it's as if it's in space, because we literally would not be able to access it without disassembling the entire thing.
Yeah. So we are now in the center of the detector. So this is what we call YB0 for yoke barrel. And this is very much the center of the detector. What's also interesting about the yoke barrel 0 is that it contains the magnet and it doesn't move. So there are there's 2 slices for the barrel and 3 slices for the end cap for each side. And these can move, but the barrel 0 that contains the magnet, it doesn't move. It stays here. And this is, again, as Claire was saying, this is the heaviest part, which is 2,000 tons. And the detector is built around it. You can really almost say that CMS is, you know, we have our entire detector that fits inside the magnet, and then everything else outside is dedicated to muons, right? So we have this yoke barrel that, or the yoke itself is 12,500 tons of steel that sort of channels or redirects the magnetic field outside the magnet so that we can generate 2 Tesla outside the magnet versus 3.8 Tesla inside the magnet. And then outside of the magnet, we have 4 types of muon detectors that basically tell us information about the muons that are coming out of our detector. That's really the only particle that punches through the magnet. If you if you ignore neutrinos, which we don't measure actually, we don't measure them directly. So yeah, inside of the magnet, we have the tracking and the calorimetry, and then outside the magnet, we have all the muon systems.
If you like cabling, you'd have a field day one of these
Yeah,
things.
you can see here, the cables are nice and tidy. Your mileage may vary. So there are there's some cabling that needs to be very tidy. So you can see here, this doesn't happen by accident, by the way. This has to be designed. So we need to make sure that there is room for all the cables that we need. This is ongoing for the upgrade, right? So we're designing these new detectors that are going to come in. And, you know, we need to design a way to have all these services. We see all these cables coming in, and these could be low voltage, high voltage, but there's also potentially cooling that needs to go in. There's potentially gas that needs to be provided for the muon system. For example, there's a specific mixture of gases that are required for the muon system. And you can see this is all tidy, but that's by design, of course.
Some of those look like optical cables as well, you know, so they're fiber optics. So you can't just accidentally bump into one of them and then you break the cable and then
we
you
can
don't.
we can also point out, so yes, there's a lot of fiber optics, but one other thing that's worth pointing out is you can maybe see this, we call this a cable chain. So you can see that these cables go around this bend, and they are in this cable chain so that we can move the slices without having to disconnect any of these cables. And that's, you know, it sounds trivial, I guess, but if we had to disconnect these cables, this would add like a month, and it would add so much complexity. So you don't want to disconnect the cables if you don't have to, and this is what allows us to move the slices without having to disconnect all these cables.
That's a really interesting point. Imagine, I guess, like doing all of the electrical wiring in your house, but thinking ahead that at some point in time, you're going to want to cut your house up and into slices and move all the slices apart in various configurations without disconnecting any of your electrical wiring. That's sort of the thing we're talking about. Yeah.
So this is actually a very cool view. I haven't been to the plus side in a while, but what you see right now is very interesting. You can see there's still work ongoing. But what you can also see, I mentioned in the other side that the shielding needs to be unfolded, and you can see what that looks like here. But on top of that, we have the new forward shielding. Again, forward refers to the area, so this is downstream of the proton collisions. And you can see that there are these orange blocks that are surrounding the cylindrical shielding, and it's not done yet. So there's still more shielding to go on top of this of the sphere of the cylindrical orange shielding. So yeah, the new forward shielding is meant to reduce the backgrounds in our detector, and what that means is there's two aspects to this. So, but just to keep it simple, right? So when the protons are coming in from that side of the cavern, from over here, and just on the other side of that wall, we have a set of magnets. So we call these the triplet magnets, the inner triplets, and these will focus the particles, or really like yeah, let's say just focus the particles like in very much like in an analogy with optics. They will focus the beam, and when that happens, these charged particles will emit some radiation. This is called synchrotron radiation. Anytime you change the direction of charged particles, they will emit this type of, well, relativistic charged particles, I should say. So anyway, we have to shield our detector from this incoming radiation. We only want the proton beams, not the associated radiation that comes with them, which is not as bad as electrons, of course, but we still get this type of radiation. And yeah, this shielding will become much more important for the upgrade that we've referred to a few times. So the upgrade is coming up after 2026, in, let's say, towards the middle of 2026. We expect the LHC to shut down for a period of about 4 years or so. And during that time, we will upgrade CMS. I mentioned the two of the main upgrades. So the NCAP calorimeter which is just here in inside and a few layers into our detector. And then the inner tracker, which is the innermost part of our detector, that will be replaced entirely. There's several more upgrades in CMS, but also the LHC has to upgrade their equipment. So in fact, those triplet magnets that I mentioned are just in the wall here to our left. Those will be replaced, and they need to actually incorporate a new type of superconducting material. So in our systems, in our superconducting systems, we typically use niobium titanium. But for these magnets, they will be using niobium tin, which is a new type of superconducting material that can generate higher magnetic fields, but it's more difficult to work with. It's a material that's more brittle. But that will generate higher magnetic fields, so we can focus the beam even more, and that will allow us to generate more simultaneous interactions. So we have about 1.6, or I should say 160 billion protons that are crossing 160 billion protons, and that happens as often as 25 nanoseconds apart, so up to 40 million times a second. You can see the picture here that is simulating, or it's a representation of these types of interactions. You can see there's many vertices. And at the moment in CMS and Atlas, we can have as much as 60 to 65 interactions per crossing. That's our limit for many reasons. Reasons that are, these limits involve the LHC and the triplet magnets, but they also involve our ability to record all that information. So we want to take that number from about 60 to about 200, or perhaps even 300. And that upgrade involves all of these projects that I mentioned of enormous complexity. And as I just said, we need to also digest and record this information. So our trigger system, which is the way that we select the information, also needs to be massively upgraded. So we'll walk around a bit more, but I'll pass it back to you, Claire.
Sorry, what was that? Oh, so one of the reasons why we want to do this is, we discovered the Higgs. That's great. But we have only started to look into all of the information that we can learn about the Higgs boson. Now, so like, as you can see in this picture, we have about 100 billion protons passing through each other. About 65 of them actually collide. That's what you see. Each of those little yellow dots there is a proton colliding with another proton and giving some signal. Maybe one of those is something interesting, like creating a Higgs boson. And we have to, first of all, our detector has to be able to like tell the difference between this one out of the other 64 of them and pick out that really, really interesting one. Now, if we want to look at Higgs bosons, about one in every billion collision produces a Higgs. We can catch maybe one in every 10 billion. And there are certain things that we are looking for, like maybe Higgs turning into dark matter or something, that happens so rarely that even though we have been running the LHC since 2011, we still have not got enough of these Higgs boson events to be able to identify this particular rare thing from happening. And so one of the main reasons of increasing this number of collisions from 65 to 300 is just to get more and more chances of seeing these super rare events and learning a little bit more about this really cool universe that we live in. Anders, should we take some questions? I'm sure that we have a bunch of
Yes,
questions now.
that will be great. I just want to show you what's going on right now. This is actually pretty exciting.
Ooh.
So on the left here, we have this robot that is used to make a modification to the rotating shielding. The details are not super important. I guess what's interesting that's in front of you is you can see that there is this part of a crane that will be lifting this robot. So they need to move the robot because they need to modify a different part of the shielding. Yeah, this will take a while. I don't know if we're going to be able to show you the whole thing, but in the meantime, we can take some questions for sure.
Thank you. My name is Paul Shelley. I'd like to know what is the life expectancy?
Could you repeat that? There was
Can
quite
you
a lot
hear me?
of background noise.
Can you hear me?
Now we can, yes.
Okay. I'd like to know what is the life expectancy of certain. In other words, you're doing an upgrade, and it's going to take you a long time to do that.
Mhm.
Our scientific knowledge is increasing exponentially. When is this instrument going to be redundant?
Oh,
Is there
that's a great
date
question.
on that?
That's a great
So-
question. So we're talking now about an upgrade that is going to take us from about 2030 to 2040 or so. We're also thinking of what's going to happen after 2040, because by that time, the upgrade will give us more collisions per second, but we'll still be sitting at the same energy. Now, if you want to explore different parts of the universe, you actually need to increase the energy of your collisions as well, which means taking those protons and making them go even faster than they go right now inside the Large Hadron Collider. And one of the things that we are investigating right now, there's a feasibility study, is to build a underground tunnel that is 100 kilometers long. This tunnel, so the LHC will then be a feeder into the bigger tunnel when it's built. And this tunnel will go under Lake Geneva and under the mountains and around. And this will allow us to collide protons. So here we go. Here's a lovely overview of the current LHC, which you can see in the top, which is 27 kilometers, with, compared to what we're calling at the moment the FCC, the Future Circular Collider. Now, this 100-kilometer long tunnel, if we start building it in the 2040s, depending on how we construct it and what we're constructing it to collide, it might be 2070 or 2080 before we even start getting data from this thing. And so that is, that is really what we're looking for the future of collider physics at CERN. But at the same time, CERN doesn't only have the LHC. We have a bunch of we have many accelerators and even decelerators that allow us to do different types of experiments. So this is actually the current accelerator complex. So you have the LHC here, but in addition, we have the north area where we do fixed target experiments. This is where we have built prototypes for neutrino experiments that are currently under construction in the US. We have the antimatter, the antiproton decelerator at the antimatter factory. So this allows us to actually slow down antiprotons and create antimatter, so we can study antimatter, things like, does antimatter fall up or down when you drop it in gravity? And then we also have things like Isolde, which is a radioisotope production place. So this produces radioisotopes for the medical industry, as well as many other things. So so yes, right, the LHC might have a finite lifetime, but at the same time, we've got all of these other projects ongoing. And we're trying to make sure that things overlap as much as possible to ensure a continuous, production of research. Andres, is there anything else you wanted to say on that?
Yes, sure. Well, actually, I wanted to jump in and kind of talk
Cool.
about what's
Okay.
going on here, actually.
Awesome.
So
Go
you
for
can
it.
see that right now, this entire apparatus is attached to the crane. And this crane has a county lever so that they can actually lift this robot that's just over there. You can see how hard to reach it is. So it's very interesting how they have to do this whole thing. They have this yellow support with a county lever and with some weights to counterbalance. There's actually some rotations here. They're moving the counterbalance right now, which is incredibly cool, I think. I don't know if you can appreciate that, but the whole counter lever, the weights are moving to the right. And so I always,
that is very cool.
yeah, that's super cool. And I also wanted to point out a few things. So in the minus side, we're now in the plus side of the detector, and we can also see the HF, which I was talking about, which in the minus side, it's in the garage, but for the plus side, you can see it. It's inside of this green scaffolding, and then you see the yellow supports below it. And these yellow supports are in the surface for the minus side. They need to be craned down, and then we will put HF on top of it. And that's one of, whoop, wow, this is, yeah, there's the ongoing operation for the lifting, which is very, very, yeah, they have to move the counterweights. Sorry, I got interrupted, but they're just lifting now. You can see some of the action going on.
I really do appreciate a good crane lift.
We don't see this every day.
No.
Yeah, exactly.
Yeah, this is definitely not something that you see every day. So it just goes to show, right? Like, you know, you could be here working on this experiment, even if you're not a physicist, right? You could be an engineer, you could be, you know, working in logistics, just planning this sort of thing.
Yeah, and actually even these types of lifts, right? So we call this a scissor. This is a scissor lift, right? And some of our colleagues, physicists, have to use these. They have to be trained to use these when they, Noemi and Zoltan have to be on top of these things every now and then when they do maintenance for the muon system, when they replace any of the, or just make any of the connections. Anytime they need to work with the muon system, they have to use some of these scissor lifts.
Okay, but what actually is that robot thing? Because it looks like, I don't know, a lamb chop or something.
So I don't know too much about the robot itself. I think Noemi knows far more than I do, but she was telling me it's used for milling the or modifying the rotating shielding. But I don't know much more than that. Maybe Sultan can say a word.
Yeah, the thing is, let me just just change the audio settings in order to hear. So the reason for this robot was that we had to mill in a place which is radioactive. So this was not very much compatible with a person going there. So we had to find a solution. We needed to mill out a few centimeters of a pocket from the steel thing, just in order to be compatible with the next generation of the equipment behind. But the problem is that this orange stuff at the wall gets activated, especially the inner part. It's the robot worked on the inner part when it was folded out, so that's pretty radioactive. And there we didn't just simply wanted to send a human. That's the reason.
That's awesome. Thanks, little robot, for taking one for the team.
Yeah, thanks to the robot. All right, so we're gonna head back to the minus side and we're gonna go on top of the detector.
Cool. In the meantime, while they're walking, do we have another question from the audience?
Hi there.
Hi.
During your experiments, do you ever create many black holes?
Oh, we would love to create black holes. Oh,
hello.
Wow, we wish. I'll tell you a little bit more about the black holes and why it would be so cool in a second. Andres, did you want to say something about where you are now?
I was actually just saying hi. There's a visit ongoing, and
okay.
but it's again an opportunity to mention that you guys are seeing so much more of CMS than even if you were here in person. If you're in person, you're constrained to the visitors platform, but we can actually show you, walk around CMS. Maybe one of the things that's interesting is like just above, we're going upstairs here. There's a helium reservoir for our magnet. So there's the magnet is off at the moment, so I think it's safe. But when you're up here normally, you have to have self-rescue mask. So basically an oxygen mask in case of emergency. But you can see the helium reservoir right now, which is super cool. Here are the self-rescue masks. It's yeah.
It's literally cool because it's liquid helium. So,
Yeah, so this giant
Ta-da.
cylinder here, that's our helium reservoir. It even says helium on it. And this, I don't know if you see this yellow sticker on it.
Mhm.
And we have another question.
No, wait. I still have to tell you more about black holes and why it would be so cool to find them. Okay. So we have, since we've been starting, running at the LHC, we have had people looking for events that would indicate making a black hole. And unfortunately, we have not yet seen the signature of black holes. And, the thing is that even though the LHC collides protons at such high energy, we don't have enough energy density to create black holes at the LHC if gravity is the same strength on the proton's size scale as it is everywhere else in the universe, the way we measure it everywhere else. So why are we even bothering? Well, so if you really think about how the theory of gravity works, what happens is you have the strength of gravity that gets sort of spread out over the area of, well, okay, now I'm getting too technical. Let me just say that one of the only ways that you can get enough energy density using protons collided by the LHC is if gravity actually gets stronger on the tiny, tiny scales that we're talking about when we're smashing protons together. Now, how could gravity get stronger? Well, one way that gravity could get stronger is if the formula for gravity is actually slightly different to the one that we know. The one that we know comes from, the formula tells us that we have like 3 spatial dimensions in our universe. But if on these tiny, tiny proton scales, if we have extra dimensions, the upshot of that would be that gravity would get stronger on these tiny, tiny scales, and we would be able to get enough energy density to create microscopic black holes. So why we say it would be super cool to find microscopic black holes is because then if we do, that would tell us that we actually live in a universe that has additional dimensions. So that's why it's cool.
Wow.
Where do you get your stock of protons from?
Oh, cool. Andres, do you want to answer that? Where do we get our stock of protons?
Where we get, sorry, I couldn't follow.
Where do we get the protons from that collide in the LHC?
Yeah, sure. So the answer is kind of not spectacular. We actually get all the protons from a hydrogen bottle. So we have a regular hydrogen bottle, and we can take those hydrogen atoms and strip the electrons from them, and we essentially get the protons. Of course, the process is much more complicated. But these are the first stages of the LHC, and in fact, this happens with systems that we call the injectors. So you can see a photo here that Zoltan is showing of, this is LINAC 2, which has now been replaced by LINAC 4. But the principle is the same. Just before 2022, I want to say, we were using LINAC 2, and now we're using LINAC 4. But you can see here the red hydrogen bottle, and then just below it is this device called a duoplasmatron, which I don't know exactly how it works, but it has a really cool name. And so it ionizes these hydrogen atoms to extract the protons. And then it just starts accelerating and accelerating in different stages.
And a small little tank of hydrogen gas like that will produce enough protons for, what's it, 100,000 years of LHC running or something?
Few years.
Few years. Will they replace them?
So if you would calculate how much protons, how many protons you need for the operation, this bottle would serve for, I think, decades.
Cool.
However, there are some losses. There are some other experiments we serve with them. So the actual hydrogen bottle is a little bit bigger, and we change it quite often. I mean, a yearly base. But the calculation is right. This would be enough for decades if only the LHC would exist.
Yeah, protons are not our limiting factor here.
No.
Thanks.
Can I ask one more question?
No, sorry, there was a question over there. You're not wanting. No. Okay, carry on.
And I just asked, this is a very complex facility to be constructed 100 meters underground. Would it not be easier to build it on the surface, bearing in mind the size of the machinery that you're dealing with and everything else?
It would certainly be easier, but it would be a lot more expensive. When they excavated the tunnel for the LHC, this was actually done for a previous accelerator that they put in there that was operated during the 1980s. And it was cheaper to excavate 100 meters underground than it was to buy the land at the surface. Additionally, the having it underground does allow for protection from radiation and things. Soren takes the radiation safety very, very carefully. In fact, there are sensors at every exit and entrance just to make sure that and that no residual radiation gets out from the CERN sites. So yeah, it may have been easier, but it would be more expensive and less good for the environment.
The Americans
Yeah,
do.
so Claire, I
Americans,
actually like
build their accelerators on the surface. Fermilab.
exactly. I was
The
going to say the
reason
same
for
thing.
that, as Claire said, is
Oh,
the
yeah.
different legal environment. And in Europe, you do not own the soil below your building, for example. That's why it is easier to build metros. In the US, however, you own it down to the center of the earth, and that's why many people made a lot of money out of oil. That's the reason. Here at
So
we would recall exactly that photo, you would see that many tens of thousands of people are living inside the yellow ring. If we would, well, actually, even I have an apartment there. So if we would need to buy out this soil from people, this would be enormous. So we went underground. Rather.
Yeah, I was actually reading about this recently.
Yeah,
So,
sorry, I did continue.
Yeah, so I was gonna say the same thing as Sultan. So at Fermilab owns the land, so they built this ring basically on the surface. And as Sultan was saying, also the legally things are different in the US. But yeah, they have a 2 pi I think it's in miles, so it's 6.2 miles circumference tunnel, and it's all within Fermilab owned land. But at CERN, as you were showing in this picture, CERN owns the main site in Meyran, and they own the site in Prevesan, which is a large area. But then here at P5, it's not a large amount of land that CERN had to buy to build all this infrastructure. So the surface buildings, if you will, are a small part of the LHC, and then the LHC being underground, as Sultan was saying, this had legal implications. And I was reading just recently a book by Schopper, which he was the lead for the LEP project, for Large Electron Positron Collider, which actually is what the ring was built for initially. And yeah, he mentions that in France, and in Switzerland, the laws are a bit different. And they actually, so it was easier to build underground in France, in Switzerland, as opposed to France, because of what Sultan was saying, the rules regarding how the depth at which you own the land. But then on the surface, it was easier to build in France. So anyway, this is all a really interesting history, and that's part of the LHC history, but also part of LEP.
Since also we're talking about this, you might have heard Andres referring to the minus Z side and the plus Z side. So this is just, a set of coordinates so we know, which side of the detector we're on. But one of the ways I actually remember which side is which is one consequence of having the ring underground was that because you've got like the Jura Mountains on one side and the lake on the other side, we had to tilt the ring slightly. So the ring is actually tilted slightly downwards by a couple of degrees, tilting down towards the lake.
Yeah, I think it's 1.4 degrees. Yeah.
Yeah. And the detector, because the detector itself has to be perfectly perpendicular to the beam, that means that our entire 14,000 ton detector is also tilted slightly down 1.5 whatever degrees at an angle. And like it just so happens that on our detector, the plus side is the side that's slightly above ground, like slightly up, and the minus side is the one that's pointing down, and pointing towards.
So here comes the robot. Sorry to interrupt.
Oh, yeah.
I actually also, Sultan has mentioned a few times that when you're moving the slices, you have to be careful because the slant is towards this direction. So if you're moving the slices in that direction, you have to be really careful that the slice doesn't like gain on you. So so you have to be aware of this very much. Yeah.
Yeah, 1.5 degrees is not a lot unless you're moving a 2,000 ton slice.
Yeah.
Air pads.
With the air
No
pads.
friction.
So you can see the robot is making its way, and it's actually going to be
Wanna
making its
zoom
way here. You can see they're preparing the area. And here you can see some of the rotating shielding. I don't know exactly where the robot has to do the milling. Noemi is pointing. So yeah, you can see some of these holes. I assume it's near to those.
Cool.
I don't know exactly, but yeah, this is part of the activities that are ongoing, and this is of course the kind of thing we need to do when the LHC is not running. So there, every end of the year, as Claire was saying, we shut down the LHC, and we have to rush to do all this work, and it has to be carefully coordinated by technical coordination, which is in charge of organizing all this work. And it's a lot of moving parts, as you can imagine, a lot of things that need to be done and prioritized and so on. Okay, Claire, should we ask for more questions?
Absolutely.
Hello. To make a comparison with the MRI scanners that are used in the X-ray department, they use 2 Tesla magnetism usually, and they're very noisy. It's like soldiers going over a bridge when you're in an MRI scanner. Is it very noisy when everything is functional?
Oh, that's an interesting question. Because it's, if the LHC magnet makes a noise and no one's around to hear a sound, does it make sense?
This is absolutely silent. The noise in the MRI is made by the so-called XY magnets that are in addition to the main field magnets, and these are very quickly building a magnetic field and destroying, and that makes a small mechanical movement that creates the noise. By the way, this is extremely frightening. I have never tried, but
I have. It's kind of peaceful. He's like lie in this big tube, and it's like.
So maybe we can add that.
Usually the typical MRI machine's bore is only 70 centimeters in order to fit through. Here we have 6 meters.
Ah.
Once we made a joke about it. We had a visit with one of the MRI producer companies visitors. And I mentioned, oh yeah, I'm here. So I mentioned them that we could use African elephants even inside if it was an
The
MRI.
LHC.
Yeah, the CMS magnet.
Oh yeah,
That would withstand it. So not just 70 centimeters. Come on. This is, by the way, the biggest superconductive magnet bore that has ever been built in the human history. Yeah, one of the biggest.
Andres, I think
So
you had a follow-up.
Yeah, just to also mention, well, first of all, you can see the robot making its way, which is super cool. Yeah, but I was also gonna say, I think right now the microphone that I'm using has a very nice noise canceling, but despite the fact that it is generally quiet, I mean, this is not as loud as an MRI machine, for example, but in the CMS cavern, there is quite a bit of noise, but mostly this is due to fans and pumps and cooling. So it's not
It's more
exactly
of a
because of the
constant hum, right?
exactly.
Rather than
In fact, Zoltan told me at some point there's an interesting project he's working on. I don't know if this is implemented already to use the sound in the CMS cavern as a debugging tool, right? So if all of a sudden there's a change in the background notes, maybe Zoltan can tell us more.
Well, actually, we are thinking of having that. That's what I have to turn down. Sorry, I hear myself back in the monitor. So indeed, yeah, this could be a very good tool because you can imagine that if a pump fails, that creates a different pitch. So this is something that we could look for in this system. By the way, again, one more anecdote from my praxis in the past as well. So that is quite a huge noise, as understood, due to the fans of the racks, the cooling of the racks. We have something like 200 racks in that zone, so that's pretty large. And whenever I enter during the Christmas time and everything is off, it is that silent.
Eerily quiet.
And that makes me scared indeed. So something in back of my mind just rings a little bell that alert, something is going wrong, alert. So
our detector is sleeping. Well,
the detector is sleeping, and our state of mind is sometimes interesting. Yeah.
It's funny, like what you just get used to as normal, right?
Okay, Claire, maybe we will start making our way to the surface.
Sounds good.
Unless there's anything else you want to see.
Is there anything else underground that people want to see?
I don't know if you can see me.
No, come over this way.
Come over this way. Oh, there we are. Okay.
There we are.
The screen. Hi, Claire.
Hi.
This is fascinating. We have exceeded our time a little bit, but I know there's still a lot of interest. I wonder if we could just for a minute call it a day so people who have to leave can leave and others who have more questions can stay on afterwards. Can we do that? Does that suit?
Absolutely. That's
a
good
short
for us.
hiatus.
Sure, absolutely.
Will you thank Claire in the meantime, and then we can carry on for those who want to? Oh, you can't do it. I think from the some response we've had here, you have just created so many wonderful visual pictures for us, excitement. I have loved the passion and the excitement that you and your team, Zoltan and everybody, you're so excited about what you do. And you think about the huge amount of work and effort that is going into your work in CERN, and we can see the astounding amount of money that it must cost and the astonishing amount of electricity that it must use, and how everything is so worth it because we have people like you to participate, to drive it, and to take it to its next level. So at the end of a 3A, we always give the speaker a gift. And the gift is always a bottle of wine. Okay.
Awesome.
It's always a fine South African wine for obvious reasons. So we have declared this bottle of wine virtual.
Okay.
And we are sending it to you over the airwaves so that you and the team enjoy a virtual glass of wine together at the end of the evening. And we will do the same thing, but we'll drink the bottle.
Okay. We will toast with our coffee cups now, and save the wine for after robots have finished moving around and
Sure.
dancing.
Well, that was absolutely divine. Thank you. Thank you so very, very much. And I know that there are loads more questions, so
Absolutely.
as long as we can carry on. Bless you all.
Absolutely. Cool. Thanks, everyone.
Thank you.
Questions?
Thanks, Matt. A simple question, what is a Higgs boson and why is it so important to find one?
Fantastic question. So you know how you have the periodic table of the elements, right? And it basically is the collection of all of the elements. And when you put the elements together, you can build up any molecule that we have on Earth. In particle physics, we have this thing called the standard model. And the standard model is basically like the periodic table of particle physics. It's the set of the most fundamental building blocks that make up everything in the universe. So we have the quarks that make up protons and neutrons, and we have things like the electron and its heavier cousins, muons, blah, 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 blah. And we also have particles like the photon, which carries electromagnetic force and stuff. So this collection is called the standard model of particle physics. And basically up until 2012, this collection of particles had no, like there was no proof. Well, this collection of particles if you only looked at that collection on its own, then all of those particles had no mass. And that's clearly not the universe we live in, because there we go. Here we've got a picture of our standard model of elementary particles here. So before we had the Higgs boson, just the collection of particles that you see in purple, green, and red, if you only have those, then those particles have zero mass. And that is not the universe that we live in. Things have mass, right? This, I let go, it falls in, it has mass. So back in the 1960s, a bunch of theorists were trying to come up with a formalism that describes why these particles have mass. And there were actually a number of them that at the same time came up with what we call the BEH theory, which states that the universe lives in a field. And so the different way that the particles move through the field is what we see as mass. So let me give an analogy. So imagine that you are sitting on the side of an Olympic swimming pool, and you watch Roland Schoeman dive into the pool and zip across, and he goes super fast, right? And then at the same time, you watch me jump in, and I'm not a particularly fast swimmer, so I kind of splash a bit more and I go much slower across. Now imagine that you're watching this, but you cannot see the water in the pool. You might look at this and you say, okay, well, Roland Schoeman was going fast, so that maybe he has very little mass, whereas Claire was going slowly, so maybe she has a lot more mass. That is basically the way that the Higgs field, or what we're calling the Higgs field, the BEH field, works. Is we can't see the field, we see its effects, and the effect is what we call mass. Now, just like the water in the pool is made up of little things that we call water molecules, the Higgs field can be made up, is made up of Higgs particles, Higgs bosons. And so what we can do is when we collide protons, it's basically like, you know, like splashing the water in the pool, and you get like a little splash of water coming out. That's what we're doing. We get like a little splash of Higgs boson. So the Higgs boson is basically the particle that is associated with the field that gives everything mass. That makes sense. Did you say no?
And any other questions? No. And Claire, just a question from me. I know that the LHC is 100 meters below ground, but the cavernous area that you are functioning in, can you give us some indication of how many meters tall it is? You know, the actual tunnel that you are working in down there?
So the cavern that holds the CMS detector, so it goes down to the ground, which is about almost 100 meters. The level of the LHC beam pipe is at about 86 meters down, and so the cavern is, you know, that's another like 14 or so 15 meters above that. So the cavern's maybe about 30 meters from top to bottom. Yeah.
Thank you.
Ah, we're back.
Yeah, we are back.
Do we have another question?
Yeah, I just want to ask a question about the spending of money on research. Where do you see the fruits coming down the line? Because take a pharmaceutical company, they spend money in finding a drug that will cure something or other. Or some other country does nuclear bombs so they can dominate. I mean, where do you get the spending of all this money when we've got such shortages in the world?
So that's a really, really important question. And you know, when we say something like the LHC cost 6 billion to build, that sounds like a lot of money. But if you think about it, we started building this thing in the 1990s or whatever. It's now 2025. We're going until the 2040s with this thing. If you spread that cost out over the people in Europe, it amounts to something like the cost of one cappuccino a year.
Yes.
Per person. Which, let's be honest, I don't think that one cappuccino a year is a huge amount of money to contribute. What do we get out of it? Well, the fact that I am talking to you right now via the World Wide Web protocol, this is something that was developed at CERN so that scientists could communicate with each other. And CERN gave this protocol for free to the world. And so now we can talk to each other. We can have these virtual visits. Everybody who has, you know, one of these things in their pockets is able to be connected to essentially every other human being on the planet. Other spin-offs from this, the magnets that we use, the magnet technology is what goes into things like MRI machines. Most accelerators on the planet are not in research labs, but in hospitals. The nuclear isotope program produces nuclear isotopes for use in cancer therapy and that sort of things. So So it sounds like it's a huge amount of money, but really it's not. And one of the things in particular that CERN has always done is said that every amount of like every result that comes out of CERN has already been paid for by the public, which is why like all of our results get published in open access journals. Everything is open and free. If you come to a visit to CERN, you don't have to pay a cent. You can visit the experiments, you can visit the exhibitions, and all of that, and it's all completely free because this has already been prepaid by people with their taxes. So this is another way that, you know, it's not a money-making scheme. But I think also finally, you know, with any type of research activity, any type of fundamental research like this, is that, you know, everything that we're doing is going to have some spin-off. That is a guarantee. The thing that we can't tell you is what that spin-off will be or when it will come. That's not how fundamental research works, but it is always going to be like a return on investment. Do you have anything else you want to add?
Well, if there's anything I would add is that I want to echo something you mentioned much earlier on today, which is that it's research. If we knew what we were doing, it wouldn't be called research. But I also would like to, I like to refer to it as exploration. What we do is really just exploring the smallest scales and testing our understanding of it. We try to describe it, characterize it, predict it, and we are just exploring energy regimes and scales that we haven't explored before. So that's how I like to think about it.
It's sort of like, why do people climb Mount Everest, or why do people, you know, explore the deepest parts of the ocean and push boundaries like that? It's because we can and we want to explore that,
and we should,
like
and
the nature of humanity.
I think naturally you have spin-ups, as you said, right?
Yeah.
So I think that's how I like to think about it. We don't know what's gonna come of it, but we certainly need to do that. We need this type of research.
Sure. Like when we started understanding quantum mechanics, right, the way that the universe works on small scales, that allowed us to build things like computers and smartphones and stuff. So when we start really understanding the Higgs mechanism more and more, who knows what is going to come of that. So
yeah, there's this famous quote, when the electron was discovered, somebody in the UK government asked, what is this good for? And the response was, I don't know, but I know someday you will tax it.
Yeah, there we go.
Actually, that is another example. We often tell this. I think it comes from Max, but that is another thing. If you recall your mobile phone, you have a GPS in there.
Mm-hmm.
The GPS very heavily relies on the theory of gravity by Einstein.
Mm-hmm.
You know, the general relativity that very few people understand. I tried to learn it several times. Okay, so anyway, when this was made by Einstein in 1915, it had absolutely no application. Yeah. This was purely a theoretical thing that has been verified by astronomical observations later, but nobody knew what it is good for until the GPS came. Without using the general relativity in the GPS softwares, we would lose a meter in every minute from the accuracy. Yeah. So it means that very soon it would be completely useless. This is a very important thing. That's why the basic research that we are talking about is important in the life.
But it's not why we do it.
That's not what. No,
We
we do
do
it
it
'cause
to explore, you know?
we do it because
Yeah,
it's fun.
exactly.
And we
This-
get to watch robots flying around on trains.
There is also another example, and this was Christopher Columbus. You know, he had a theory. Well, actually, that was a common theory that if you sail to the west, you get to India.
Hmm.
So he made an experiment with the three boats, among them Santa Maria, and they sailed out to the west, and they found something that was actually not India.
No, but the theory was correct. You just
The theory-
didn't bank on there being an entire continent. in
Exactly.
between.
So they found something completely
Different,
interesting,
yeah.
completely unexpected. So this is also a mandate of these experiments that we think we talked about the black holes, we talked about the dark matter, we talked about the standard model of particle physics. Or it might happen that we find something absolutely interesting.
Yeah.
Right. May I step in here now? Claire and your team, your mum thanked you so nicely just now, but I'm afraid there was so much noise as people were leaving that you possibly didn't hear it all. So I just want to reiterate what she said and to thank you all for taking us into another world. And possibly we've all now got a better understanding of particle physics, dare I say that, or at least something of what happens at CERN, and we can speak with a little bit of authority going forward. But thank you so much for entertaining us, instructing us, and just making such a wonderful meeting. Thank you very much.
Thank you
Thank
so
you.
much to all of you for the fantastic questions, and I'm really glad you enjoyed it. Thank you, Andres, for your amazing underground tour, to Noemi for doing all the good camera work so that we could see that cool robot and everything, to Zoltan as well for being here.
Sticking my nose in everything.
No, it's awesome. It's thank you so much to everybody involved, and it was great to see you all. Bye.
Thank you. Have a nice day. Bye.
Bye.
Bye. Bye.